Okay, attempting once more to write out the expression a little more clearly. This is just the expression we ended up with on the last video, and it should be clear then. I've moved the delta theta over here because, of course, delta theta is going to become our d theta when we go to the integral. Here's the expression. I'm not going to read it to you. It's the same as the expression that we ended up with previously. This approaches as we let our delta thetas go to 0 and sum them all up, and I didn't write out all the details of that summation. I, A, K prime, all being constants, come out of the integral. Delta theta becomes d theta, and the theta stars become thetas, and here's our integral. Okay? So, now, don't know what that negative infinity is doing right there, but I do know what it's doing. I started to write out the integral here, realized I didn't have room, and rewrote it down here. And then before I did the video, I just kind of wiped all that out. Okay, you can still see some of the water drying right there. Okay. In any case, here's our integral. Now, let's just keep our wits about us and look at this integral. Okay, first of all, the integral has a d theta here. Okay, so we're integrating with respect to theta. Our only theta dependence is in the I component and the j component. And I'll observe that if we integrate from 0 to 2 pi, and of course we integrate from 0 to 2 pi because we're integrating around the whole loop. Theta has to change by 2 pi to give us the whole loop. Okay? If we integrate cosine theta with respect to theta from 0 to 2 pi, what do we get? We get 0. You can understand that, full cycle of the cosine function has as much area above the axis as it does below the axis. Alternatively, the antiderivative is the sine of theta, and the sine of 0 and the sine of 2 pi are both 0, so we're going to get 0 in that integral. Now, sine theta, same thing. If we think of the graph, we get a whole cycle, so the integral of the whole cycle corresponding to the area above minus the area below gives us 0. The antiderivative is negative cosine theta. At 0, negative cosine theta, well, cosine theta is 1 here and here, so negative cosine theta would be negative 1 and negative 1. There's no change in the value of cosine theta, so that the integral is 0. So that all this goes to 0, so that the integral just becomes the integral of AK over this denominator times d theta. But now, this has no theta dependence, and this has no theta dependence. So I write down an intermediate step, factor out the AK, and I get a squared k prime, and it looks like I didn't write my k vector. Okay, so k prime times the k vector, and I didn't put it over here writing down k prime. Felt like I'd written the k vector. And actually that's just really wrong. It's kind of interesting. We'll have to go back and figure out why this came out the way it did. Never mind, it's right. Okay. Confusing this situation with that situation. I suddenly realized that the vector was going to be parallel to the z-axis, and I lost track of what I was thinking about. Okay, well, it has to be parallel to the z-axis in this configuration. Okay, in any case, we get this, and we have a d theta over a squared plus z squared to the 3/2. I don't know what I was thinking when I wrote out this step, because that a squared plus z squared to the 3/2 is also constant. I could have factored it out immediately and had it here. That would leave us with just the integral from 0 to 2 pi of d theta, which is just equal to 2 pi. So what do we get? We get 2 pi times this over this, times the k vector. That's the field. It's a vertical field straight up the z-axis. All the i's and j's go away, as they must if you think about the symmetry of the situation, but we'll talk about that in a few minutes. The point being that there's a symmetry argument that allows us to ignore everything but the k component of the delta b, meaning that all we have to do is integrate ak over this times delta theta. We don't even really have to integrate in order to get the result. And we'll look at that simple result after we've done a couple of other things.